So we can have some alternatives or some variations to the vanilla version of the k-nearest neighbor model. The first thing is like we can use a weighted distance to find the neighbors. So in this case, for example, if we want to classify this black point, we see that we have 6 neighbors. 2 of them are red and 4 are blue. But the red ones are much closer to this point than the blue ones. So if we use a 6 nearest neighbor classifier, then the classification for this point would be blue. But seems that it's not what we want, because we see that the red points are much closer. So somehow we should use that information for the classification. So this is an example, right? Because if we use k equal to 4 and we want to classify this yellow point, we want that anyway the class is red, because we see that the red data points are much closer than the green ones. Even if we were to use k equal to 7, we would like that the classifier predicts as a class the red color, because we know that the green points are not as close as the red data points. So how we can get this effect? By weighting the distance to the neighbors. These are two of the most common alternatives. For example, we can weight according to 1 divided by the distance, or to use an exponential function. If we use 1 divided by d, we are going to penalize linearly to the neighbors. For example, if I am 1 meter away from a given data point that we want to classify, and if I move away 1 extra meter, I'm going to be penalized the same way as if I was 2 meters away from the neighbor and then I move away another meter. So in general, in practice, what works better is to use an exponentially weighted distance to the neighbors. Because if we are a really close neighbor and we move away 1 meter, we want to be penalized stronger as if I was a really far neighbor and then I move away another meter, right? It is like when my closest friends throw me under the bus, I'm gonna feel much worse compared to the case when people that are not close friends are throwing me under the bus, right? So that analogy also applies for data. So again, to summarize, the main difference between these two alternatives is like this one is going to penalize the neighbors regardless of their distance to the main point, because it's using a linear penalization. But in this case, this is going to use an exponential penalization. It means that the weight is going to exponentially decay as we are moving farther from the data point we want to classify. And how we use these weights? Well, before, without the weight, we just go over the neighbors of a given data point xi, and then we calculate or we get the class and we select the majority class. But now we are going to multiply each of the classes by a weight, such that when the weight is bigger, that class is going to be considered the most. And how we calculate each of the weight is just exactly the ways we had here from this formula, but normalized by the weights of the neighbors. In that case, we are going to have that the sum of the weights is equal to 1. What we can also do is to weigh the dimensions, because sometimes one dimension is more important than another one. For example, here, maybe this vertical axis is going to be much more important than the horizontal one. So in this case, we need to assign a bigger weight to this axis and have a better calculus of the similarity metric. In general, it's kind of hard to know what should be the weight for a given dimension. But in some practical cases, the domain experts can come up with a weight vector for the dimensions according to their knowledge or their previous studies, and then we can apply those weights into the calculus of the distance. Here is a very simple example. We can weight the Euclidean distance by applying these W values to each of the differences among the different variables, right? So we can see that this formula is exactly the same as the known Euclidean distance, but every time we go over one dimension, we must apply a weight. So for the more important dimensions, this weight is going to be higher, and for the less important dimensions, these weights are going to be lower. In this case, we can bias the Euclidean distance towards a space that is more suitable for some specific real cases. some important things to consider is like how many neighbors. That's a very important parameter we need to define before we apply this classification model. What distance metric to use? Is it Euclidean? Well, in practice, we can use an Euclidean metric when we have continuous variable. But if we have some variables that are discrete or binary, then we're going to have to design a very specific metric for our case. Another question is that shall we use weights? In practice, in my experience, adding weights to the neighbors always improve the results of the classifier. But regarding the weights to the dimensions, we only must use weights to the dimensions if we really know those weights or we have a clear explanation on why those weights are suitable for the dimensions we have in place. Another important thing is how long we can wait for classification in production time. Right? Because if we decide to use a k-nearest neighbor classifier, it means that we have the time to wait for the classification of a new data point, considering that it's going to be necessary to compute the neighbors for every single classification. So maybe in production, we want online predictions or real-time classifications. In that situation, it is very likely that the nearest neighbor model is not going to be suitable for our context, and we are going to have to use another classifier that better spends time during training, but it is much faster for classification in production. This is an interesting topic in machine learning and data science, which is the curse of dimensionality. In general, things get really bad when we have very high dimensions. It means that most of our models will not work, and we will have to do some sort of pre-processing or treatment to the space such that we decrease the dimensions and we have a more compact representation of the data in order to apply our classifiers. And the k-nearest neighbor is not an exception. We can see here that it suffers from the same problem of the curse of dimensionality. For you to have an understanding of this problem, imagine we have a data cube like the one in the left side. We can think that if we have a bunch of uniform points inside this cube, if we were to move or to increase this blue cube that is inside the bigger one, if we wanted to grab 50% of the data points within this cube, our intuition tells us that the blue cube should be able to reach 50% of the size of the black cube in every dimension, right? So our intuition is telling us, you want to grab 50% of the points inside the cube. Okay, grow a blue cube whose size is 50% on every axis. Well, that intuition is wrong. Actually, that only works for one dimension. If we have one-dimensional data, then in order to grab 50% of the uniform points that live within that dimension, we need to grow a blue line that exactly matches half of the size of the black line here. But as soon as we start increasing the dimension, that situation changes. Actually, for 10 dimensions, in order to reach just 10% of the uniform data points within the 10-dimensional cube, on each of the dimensions, we have to cover 80% of the axis. So again, in one dimension, in order to grab 10% of the uniform data points, we just need to have a blue line that is 10% of the size of the black line. But if we have 10 dimensions, then we're going to have to grab 80% of the size of the axis on every of the 10 axes, and we are going to just grab 10% of the uniform data points. And this is what we see in the right plot here. When we have one dimension, the size of the blue cube grows linearly with the size of the data points we want to grab. But as soon as the number of dimensions increase, for example, when dimension is 10, in order to grab more or less 10% of the uniform data points, we need to cover 80% of the space. So things become much worse as the dimensions increase. Mostly it means that if in order to grab a very small fraction of the uniform data points in high dimensions, we are going to have to cover almost 100% of all the axes in high dimensions. So this is a classical example to have a sense of the problem in high dimensionality space. In general, in high dimensions, all the pairs of data points have the same distance among them. We start losing the sense of distance because we have too many dimensions in place. So it's very important that we treat that problem and we are able to compress the high dimensionality space into smaller one in order to apply models like the k-nearest neighbor. So some remarks: recall that KNN does not use training time. This is why it is called a lazy learner. Most of the time is used during classification. And KNN is a non-parametric model. We are going to cover this concept in videos later, but non-parametric, it doesn't really mean that it doesn't have parameters. Actually, it has parameters. For example, K is a parameter of the model, but a non-parametric model means that the bigger the size of the training set, then in easy words, it means that we don't have a set of parameters that it is finite or limited regardless the size of the training set. For example, when we use a probability distribution that is defined by a small set of parameters, then those parameters are not going to grow with the size of the training set. That means that that model is parametric. In our case, the execution time of the KNN will be affected by the size of the training set. And this is why this model is non-parametric. We can also see that the value of K can be considered as an hyperparameter for the k-nearest neighbor model. And the actual parameters that the model uses strongly depend on the training instances, because that is what essentially affects in the prediction time. So the bigger the training set, then at testing time, the model will change because KNN needs to grab the neighbors of the testing instances. So this is why this model cannot just rely in a set of fixed parameters to classify new testing points, as in the case of the linear regression, in where after we have the beta values, then we don't need anymore the training case to perform the prediction.